Welcome to today's virtual book launch. Subsurface Consultants and Associates is hosting the co-authors of Applied Three-Dimensional Subsurface Geological Mapping with Structural Methods. This is the third edition. And so we're pleased to introduce you today to Dr. Richard Breneke, James Breneke, and David Metzner. And we're looking forward to their talk as they describe how they edited the third edition of this famous book. Jim Breneke will be our first author who will be speaking, and he'll talk a little bit about the reasons for updating the book. He'll show you some of the new material that's included in the third edition, and he'll talk about how it ties to one of SCA's flagship courses, the Applied Subsurface Geological Mapping course. He'll be followed by Dave Metzner. Dave is also an author and SCA consultant who will be talking about the inclusion of interpretation of 3D seismic and workstation techniques. Dave has experience with both conventional and unconventional reservoirs around the world, so he'll be showing you some examples from some of his experiences. And they'll be followed up by Dick Bitschke, who is the lead author for this book updating project, and he'll be describing some of the contributions that he made to the book. So let's start with Jim Breneke. Jim is a geologist with more than 40 years experience. He started his career with Shell and has worked in regions around the world. He joined SCA in 1994, where he worked with some of these original authors of the book, including the late Van Tierpak, and worked on various projects for SCA, where he served as Vice President of Geoscience and Engineering. He joined BP in 2006 and worked on several fields in the Gulf of Mexico deep water, and currently teaches now Applied Subsurface Geological Mapping for SCA. Jim, as we're thinking about this book, can you tell us a little bit about why we needed to have a third edition for this famous textbook?
Well, Susan, there's a lot of new material that has come since 2003, when the second edition was published. And so there was new material that I think all three of us wanted to incorporate into the textbook. Secondly, we have moved totally to a workstation environment for almost everyone. And there is a perception in some people's mind that the old techniques that are in the textbook don't really apply to the workstation environment. And we needed to make clear that they do apply, and occasionally you have to make some minor adjustments in order to take advantage of the workstation. Finally, over the last 25 years, we've had a revolution in transitioning from vertical wells to horizontal wells. And sometimes the techniques that we've used in the past for vertical wells need to be modified slightly for horizontal wells. So those were three of my reasons, and I know Dick and Dave had some others. But those were things I was anxious to accomplish.
So Jim, can you give us some examples of some of the new material that's in the new third edition?
Well, one of the things that I was very interested in was to talk about the measurement of depth in wells. Traditionally, that has been done by wireline logs. And if you show the next slide, we see that depth in wireline logs and depth in LWD logs is usually not the same. Depth in wireline logs is measured by recording the length of the wireline cable, and depth in LWD logs is by recording the amount of drill pipe in the hole. And the forces that act on wireline cable and act on drill pipe are different. They respond differently, and therefore they give you a different example. In this particular case, we see a pay sand that was logged 20 foot higher in LWD data than it was in wireline data. And if you go to the next slide, you see that this is really very typical. LWD logs are almost always shallower than wireline logs by 20 to 50 feet in most cases. So if you're trying to make an accurate structure map and you mix wireline logs and LWD logs, you're mixing in 20 to 50 feet of variability in depth that kind of defeats the purpose of making a very, very fine scale structure map. So we needed to talk about that, and that was one of the new things that I added to the third edition.
Thanks, Jim. Can you give me an example of adapting an old technique to the workstation?
Yes, Susan, if you show the next slide, this is an example of using restored tops. Restored tops are very, very powerful in mapping faulted structures. And they are from wells where the horizon that you're trying to map has been faulted out and is not present in the well. So you try to estimate where the top would be if the fault didn't exist. There are two problems on the workstation. One is you end up with two tops for the same horizon in the well. And many software packages don't handle repeated horizons very easily. The second problem is that the restored tops occur in the fault gap. And if you put a fault polygon on your map and tell the computer to contour your data, you've told it to ignore the data in the fault gap. And that's where your restored tops are. So in the book, I explain one approach, which is to enter the restored tops as dummy wells or pseudo wells or digital control points and move them slightly out of the fault gap so that the workstation can use them as part of its contouring.
Great. Can you give me an example of how horizontal wells are used differently than vertical wells?
Yes, Susan, if you go to the next slide, this is an example of dealing with something that in the book we call multi-surface stacking. That is where you map a shallow horizon and then you use the shape of that shallow horizon plus the isochore thickness of the intervening strata to map successively deeper horizons. It gives you more data than you have if you just map the deeper horizons with the data on those horizons alone. But as you can see in this slide, when you have a horizontal well, the data doesn't really line up very easily. In this case, the top map, the red horizon, was accurately mapped, and the top in the well came in as expected. But the two tops that were encountered for the blue horizon came in low to the existing maps. And the top for the green horizon came in even lower. Now, if you just try and remap using these tops, what you'll end up doing is changing the structure of the blue horizon and changing the structure of the green horizon, but not changing the structure of the red horizon. And that will cause unrealistic changes in the unit thickness of the intervening stratigraphy. A group at Saudi Aramco came up with a very interesting technique for dealing with this. What they do is they look at the mistie for their different tops, and they put control points on their reference horizon, in this case, the red horizon. That distance from the reference horizon, then they recontour the reference horizon, and they use the stacking principle to conform the deeper horizons to the shape of the shallow horizon. And that gives you a picture like the next slide. So here we have corrected the red horizon, and we have kept the isochore thickness that we expect for the various units. And the result is we have a much more accurate red horizon, and we also tie both the blue and the green horizon. And if you're drilling a horizontal well and trying to stay in a thin zone, having an accurate structure map is very, very helpful in drilling efficient horizontal wells.
Sounds like a very useful technique. You're one of the instructors for SCA's Applied Subsurface Geological Mapping course, and has this course been updated to reflect the changes in the third edition?
Susan, yes, it has. The other instructors and I have gotten together, and we have taken some of the key additions out of the third edition and incorporated them into the current Applied Subsurface Geologic Mapping class. Now, there's a lot more information in the book than we have time to cover in the class. And we go into a lot more detail on more subjects in the book than we do in the class. But on some of the key subjects in the class, we go into more detail than we go into in the book. So it's an updated class. It reflects some of the new material in the book, and I think it does so very thoroughly.
So even if someone took the class 10 years ago, they might want to come back and take a refresher.
They might.
Great, thank you. So next, let's talk to Dave Metzner. Dave began his career as a geophysicist, working in oil and gas prospects around the world. He had authored Chapter 9 in the second edition of Applied Subsurface Geological Mapping, where he really brought it up to date with practical workstation-based advice. And in this latest edition, he continues to use the latest best practices in industry and technology. They participated in many discoveries around the world, both in the Gulf of Mexico and in Latin America. He's worked both conventional and unconventional reservoirs, most recently having worked for Pioneer National Resources. Dave today is a consultant at Crossroads Geoscience Consulting, and he's been a member of APG and SEG since the beginning of his career. So Dave, this third edition, Chapter 9, has been completely updated. Tell us your thoughts about why you chose to completely overhaul it.
Yeah, thanks, Susan. The 3D workstation hardware and software and interpretation techniques have evolved significantly since the second edition was published in 2003. Horizontal plays have emerged to become prominent in today's industry. 3D visualization and horizon auto tracking are now the norm for interpreters. So we have increased speed and efficiency, which allows accurate interpretations, which remain compatible with the overall principles taught in this book. Chapter 9 has been completely updated using examples from 4 of the most prolific horizontal plays in the world. These include the Wolfcamp, the Haynesville, the Marcellus, and the Eagle Ford.
So can you show some examples of 3D visualization and how it has improved 3D seismic interpretation?
Yes, in the next slides, we can show some of these examples. Here we see data reconnaissance using an auto-tracked horizon. These can be done very quickly, and it helps you easily spot the structural trends in the data. Both examples here, one is extensional from the Haynesville, the other is from compressional play in the Marcellus. And then you can see that the faults are very well defined and the structure is emerging even very early in the interpretation process. And in the next slide, we're looking at an Eagle Ford example where in this case, the Eagle Ford wells are susceptible to faulting where that impacts the commerciality of the well. And spotting these faults in the seismic data is one of the main tasks that we have as interpreters. So using visualization and in this case, a light shading technique, we can see how the faults are enhanced in order for us to better identify them and map them. And this also allows us to interactively change the light angle so that we can optimize the display very quickly. Now, the next slide is just, to say that, we're focused on horizontal plays. Here's an example from the Midland Basin. And what we're seeing here is these techniques described in Chapter 9, they are applicable to all play types. And in addition, these methods presented in this chapter are not software specific, but should be applicable to any major application in use today. And the next slide will show the fault interpretation techniques that we outline in the chapter. This is a case from the Marcellus, and we show the process to interpret a fault surface using co-rendered seismic volumes, which means two volumes co-rendered on the same display, in this case, amplitude and coherence. And panel 4 on the lower right shows the final fault surface interpreted, displayed on an amplitude volume with a time horizon as a reference. This technique applied to multiple fault interpretations is described and documented in detail in Chapter 9.
So Dave, you added time to depth calibration in this edition of the book. Would you expand a bit on how this is important in today's work environment?
Yes, Susan. Working in depth allows better collaboration and data integration with geologists and engineers on your team. The figure on the left in the next slide shows is a time display showing time horizons, well bores displayed in time, and a seismic painted with average velocity. Now, this velocity is generated using well tops and time horizons to create a velocity volume. So when the model is applied, the velocity model is applied to the seismic data and the interpreted faults and horizons, they can be visualized in depth with any other well control and any other depth scale data, which is shown on the right. So this is allowing better collaboration amongst your team.
Thanks, Dave. Next, we'll go to Dick Breneke. And Dick was previously the chief structural geophysicist for SCA. Earlier in his career, he also served in various positions in Temple University, Drexel University, and Princeton. He worked several of the large plays in South America, and his expertise is in tectonic provinces. He's worked in overthrust belts around the world, and he's discovered oil in a number of different provinces, and he co-authored the first and second editions of the book that we're talking about today, Applied Subsurface Geological Mapping, based on his experience. Dick teaches courses in a number of areas, and he's a widely published author. He's a member of APG, HGS, and the Lafayette Geological Society. Dick, what is a lateral ramp and why is it important?
Yeah, well, lateral ramps are important because it allows you to more accurately locate the position of thrust faults underneath anticlines. And by the way, this was a technique that was only available to, it was really proprietary to the major oil companies until this publication. Here we see a lateral ramp in 3 dimensions. And you can see here that the lateral ramp dies in the left direction. Right here, the fault dies, and the top of the lateral ramp is in the tan color. The back portion is in the green, and we remove the front limb to look at the thrust fault, which is sort of in the strike direction, but not perfectly. And you can see here that the green horizon comes down and it terminates against the horizontal green fault, green horizon, I should say, and this defines one of the positions of the thrust fault. Now, the same thing is true with the yellow horizon. It comes down to the thrust fault where it terminates. And you can see from the fold here, you know, that there's a certain amount of repeated section on the slide. Now, on the next slide, we're going to be looking exactly in the dip direction, which is the top figure. And although the lateral ramp is in the strike direction, it's better imaged in the dip direction. As we can see the green horizon going down to the thrust fault and terminating against the horizontal green horizon. Same thing with the yellow horizon coming down, terminating against the fault. But remember, according to the fold here, we had some repeated section. And in the last slide, if you could go there, please, Susan. Excuse me, the first slide. We removed this section of the front limb to show the second slide, Susan. That would be this slide right here. And here you can see that we have some repeated section on the top figure. We have some repeated section on the bottom figure. Now the question is, how does this look on a 3D strike line? In fact, these figures are more accurately located on strike lines than they are dip lines. And this is kind of contrary to normal logic. So if we could look at the seismic line, please, Susan, that's the last one. So here we have a sort of a strike line in 2-way time in the strike direction. We can see the clear flank of the fold dipping downward, and the crest of the fold is sort of flat. The hanging wall is coming towards us. The footwall down here is going away. And we can locate the thrust fault by basically showing these coherent horizons going down to the flat coherent horizons from the dipping to the flat. So the thrust fault is basically located along the black line. And thus we've basically accurately located this fault for any type of missed high. And it would, all this depends on your reserves and correcting that, picking that fault correctly. Thank you, Susan.
So Dick, what other additions did you make to the third edition text?
In the 10th chapter, I have an extensive edition on how to determine structural styles. And this has always been a problem between the different structural style types. And I'd say that right now, this problem now is solved because I used about 4 different techniques to rapidly determine how it's done.
And anything else in chapter 11 that you added?
Yes, in chapter 11, what we did is in the footwall, we located an important horizon. That important horizon might contain a large amount of organic material. It might contain good fracking sands. And we have a mathematical equation to project it downward into the hanging wall. And I should end that. I use one of Dave's compressional sections, extensional sections to show how this can be done. Thank you.
Lots of collaboration went into editing this book, I'm sure.
Oh, yes.
Jim, any final comments you'd like to give us in summary?
No, I think we've covered things pretty well, Susan. The new book has a lot of new information in it. It is more explicit in how to use traditional techniques in the workstation environment, how they apply to horizontal wells. And we've incorporated that into the mapping class. So hopefully people will have an opportunity to buy the book and read it and attend the mapping class sometime in the future.
And if they attend the class, they get a copy of the book, right?
They do indeed.
Absolutely. Well, thanks for your time today, gentlemen. We look forward to reading the book. Bye now.
Thank you, Susan.